that you understand it. Before you go, I can hear the rustling already. Before you go, okay, I'm quite happy to force you to stay if you prefer. But if you look at the end of this slide presentation, there's a kind of a real case study of how we would build a block diagram representation of something, which is a speed-controlled turntable. This is what we're trying to control, is the position of a turntable. The thing that's driving it is an electric motor. What's driving the electric motor is an amplifier, and what's driving the amplifier is a difference between the angle that the angle that we want and the angle that we have. Okay, so there are at least 3, maybe 4 different pieces of that you should be able to look at in isolation and kind of get an idea what's going on. Build them into a block diagram structure and you can get a picture of what the whole system is doing. Okay, strictly speaking, I stole this picture, it's badly labelled because that's not a tacho at all. That's a position sensor, okay, so I need to correct that. So what I've got here is a system where I set a desired value for the angle, and I've got all sorts of bits of hardware that will make this turntable adopt that angular position. So this is kind of a simplified version of what you might find perhaps controlling. Let's do something topical because it's its birthday. The big radio telescopes like the one at Jodrell Bank, which I think is having its 70th birthday this year. This is schematically exactly the sort of system that you might use to make sure that your radio telescope is pointing where you want it to. Okay? And you don't want to do it manually because it's quite big and heavy, so you want an automated system to do that. So all I've done here is I've connected the battery to a variable resistance so that I can adjust the volume control, as it were, and apply a voltage to this system where that voltage represents the desired angle. Okay, so what's going into this summing junction here is my desired position expressed in volts. You can see here it's a fairly standard negative feedback arrangement. So what I'm doing is I'm comparing my desired angle to the output from my transducer, my incorrectly labelled transducer. Even if that was a tachometer, I could integrate its results, couldn't I, and get position out of it. But that should be a position sensor in there. So what I've got coming into the amplifier is an error signal. The difference between the position I want and the position I've got. I amplify that signal and use that to drive a DC motor. The output from the DC motor is applied to the mechanical bits and pieces, Jodrell Bank telescope, and hopefully turns it into the correct position. Okay. Moving towards a block diagram, that's what it looks like. So I've got my desired voltage with this gain number here simply represents the relationship between angle and voltage. I've got a subtraction going on. There's the amplifier. There's my actuator, which is the DC motor, and there's the process, which is the turntable. What do you think I'm interested in terms of the output of the motor? I'm applying it to a mechanism. This is a rotating system, and if it is a radio telescope with probably some quite magnificent numbers for its inertia, for its moment of inertia. So what output do you think I might be interested in from the DC motor? Torque. Okay. I don't really care what speed it's doing. What I do care about is the torque that it's applying to my rotating system. So then I've got the actual mechanism here, the turntable, where I'm applying a torque to this system and I'm getting an angular position out of it. You'll notice that the sensor is now correctly labelled as a potentiometer. So looking at the bits and pieces and forming it into a block diagram is where we use our engineering skill. There's the same thing, redrawn. Okay, electric motor is used in the closed loop system to control the angular position, and there it is. The load is measured by a simple pot, and the output signal is compared to produce an error. So, how do we put numbers to that? How do we turn that verbal description, it's just words at the minute, into something a bit more useful? Well, we look at each piece in turn. We've looked at the system globally and decided what bits and pieces is made from and how they're interconnected. What we need to do now is to look at each part of that system and determine its transfer function. Okay, so what I want here as an input is my desired angle theta. And because this is an electrical system, what I want to come out of that box is a voltage representing that angle. Okay? So all this box here has to contain is a constant of proportionality relating angle to voltage. So the input will be in degrees, radians, whatever you're working in, and the output will be in volts. This is a simple constant of proportionality in what units? Output is in volts, input is in, let's call it radians. So what's in there?
Radians per second.
Right, where's the seconds come from? We're not talking about speeds here, are we? Yes, it's just position, so it's volts per radian. Pretty close. So all we've got in here is a simple proportional constant that takes my radians from out there and converts them into volts. Oops, sorry, too soon. I then need to look at an amplifier, and I'm going to suggest for this one that we have really quite a simple amplifier, and I can also describe that one as a simple proportional relationship. Without going into detail, the output from this could be current or it could be voltage. In this case, if you know a little bit about DC motors, I'm actually more interested in current. So this amplifier here is another constant of proportionality relating volts in to current out. So what are the units of that one? Volts times that gives me amps. So what's the units inside the box?
Voltage over resistance equals amps.
Can't see any resistors. This is just simple maths, really. Current equals this constant times volts. So what are the units of that constant? Don't try and think too hard, it's actually really easy. I'm getting amps out of it and putting volts into it, so what are the units inside the box?
Resistance.
Nope, you're thinking too hard, I think. It's just a simple proportional relationship. Current equals some constant times voltage, so what are the units of the constant? Go on, go on. We haven't got any ohms in there. It's simple proportion. It's amps per volt, isn't it? So if I put 1 volt in times some constant number of amps per volt, I'll get some amps out of it. So try and get a better feel for the units inside these boxes. Okay, if I've got current coming out in amps, I've got volts coming in, whatever's inside the box must be in amps per volt. How much do you know about DC motors? Anything? Mechatronics last year. 2 years ago? Whenever it was. That's just an excuse for not remembering, is it? Okay, mechatronics 2 years ago. Did you guys look at DC motors?
Yeah.
Okay. What does the speed of a DC motor depend on? Voltage, somebody is saying. The speed depends on voltage. What does the torque generated depend on? That depends on the current. Okay, so what I want in here is a model of my DC motor. Current in, torque out. Okay. My load is, well, it's got a moment of inertia. It might have some friction, some damping going on in there. It might even have a spring if it tries to spring back to a fixed position. So what I've got here is torque in, position, angular position, that is position out. Okay. And then this transducer hopefully simply does, well, that's position, this is volts, so that transducer ideally has the same constant of proportionality as this one. Okay, because I'm turning theta radians into some volts, I'm turning theta outer radians into some volts. So typically those two boxes have the same number inside. Right, simplified model of DC motor. The motor torque equals some coefficient times the current. Amplifier, nice and simple, the current output equals some coefficient times the error voltage. This is our mechanical load. The torque applied is moment of inertia times angular acceleration plus damping times velocity. There's no spring. And the input demand number, or this Kp here, is that constant of proportionality that describes how I represent position electrically. I need to represent my position in radians as some number of volts. And the feedback, ideally, I'd like to make Kt the same as Kp. We know about the error signal, that's just a subtraction. So let's build a block diagram. That represents the mechanical parts of my system. The torque input, 1 upon Js squared plus Cs, as the transfer function relating torque input to position output. Km, that's simply the torque coefficient for my DC motor. Current in, torque out. A is the amplification provided by the amplifier. Volts times A gives me current. Kt is my position measuring transducer. Subtract the two to give me the error signal, and coming in from the left hand side is a voltage signal representing the position that I want. Theta in. Okay, so when you look at any sort of system, particularly in this module, when you're looking at these sort of systems, you should be able to break them down into interconnected parts, each of which we can understand. And how they connect together, we can also understand. In this case, some of this is simplified. The motor model is slightly simplified. But fundamentally, that's how we describe these more complex systems. I want that to look like a reduced block diagram. That's what some books would call the canonical form, by the way. One box in the forward path and one box in the feedback path. And there's the combined transfer function. Okay. What order is it? Second order, because there's an S squared in there. Can I make it fit a standard form? tricky because I haven't got a numbers coefficient, have I? I've just got an s squared and an s coefficient. The numbers coefficient is 0. So it's a little bit of a special case. So you could think of it, if you take out one of those s's as a common factor, outside the bracket as it were, you could think of it as a first order system with an integrator. 1 upon s times 1 over s plus something. So you've got that combination. That's the feedback. There's the closed loop transfer function, and you'll see in the closed loop it does become a standard second order that we can force into the standard form. So that's what you need to learn to do as engineers, is to look at some kind of system that you're trying to control, break it down into its constituent parts and how they're connected together, and for each of those constituent parts we should be able to come up with a model. A DC motor, a mechanical load, whatever it might be, we can break it up, and that's why the block diagram approach is so useful, because you can break things down into kind of bite-sized pieces and then reassemble it algebraically just by using the block diagram algebra rules. And we get that thing. If I apply an input of size 1 to that system, an input step, let's say, of size 1, what do you think the final value is going to be? Or better still, what would we like it to be? If I dial in, I want this to point in the direction 1 radian, what would I like the answer to be? 1 radian. I'd like it to point where I asked it to. So, what does that mean in terms of the steady state error? Do you think that's got any steady state error? What happens to the S terms in the final value theorem? They go to 0. The S terms tend to 0. If you apply a unit step input to that, and then you go through the final value theorem and set all the S terms to 0, what you're left with is 1 over 1. Which means if I put an input of size 1, I should get an output of size 1. Okay. So that, as it stands, if our system really does that, that's great. No steady state error. It should end up where I point it. S squared over omega n squared. So that number there, that coefficient, you've been doing a lot of this in the tutorial sheet, I think. That coefficient there represents 1 over omega n squared. So I can also, knowing those individual bits and pieces, I can work out the natural frequency, the undamped natural frequency of that system. So this is 1 over omega n squared. If I make J, what was J? Moment of inertia, that's right. This is my radio telescope, isn't it? If I make J larger, do you think that system's going to slow down or speed up? Slow down. This is 1 over omega n squared, so if I make J bigger, omega n gets smaller. This middle term is 2 zeta over omega n, and you can see that the denominator is the same, and the only thing affecting the zeta number in there is what we've represented the damping to be, the damping coefficient C. So we can make sense of increasingly complicated systems just by using block diagrams.